Yeah, the card. 4339. So that's 4339. You got that? Then 9116. 9316. 8181. 275.
Okay. Oh, right. I don't have this. Okay, is it all less than late?
Yeah, I'm still like at
Wait, can you
2
wave?
seconds maybe on my end. I don't know.
Okay.
Could you clap and we could just check it an
Sure.
impulse?
You might be late. No.
Oh, let me. 59889. Oh, I'm already.
Did
Yeah,
you?
mine's
Did you already
delayed
clap?
by like 4 seconds.
Okay,
I mean, that's
4's
fine,
not so
honestly.
bad.
Mine is delayed by like 20 still. I'll keep relating.
Okay.
Mine's delayed by a lot also.
And then I have to the closet doors. They're backward.
Okay, we'll see how it goes, and if it's too rough, I can either make the question timing higher or see if there's something that's a little lower. See if Twitch has lower latency. I'm not sure if it does or not. But it looks like everyone is in, and I think it should come up, even if it's not on the stream, it should come up on your Kahoot app with the questions quickly. It'll just maybe not show on the stream right away. So, okay, let's get started.
I think.
Give it a shot.
Yeah. The right side is fixed, correct? Yeah. So that.
Okay,
No, we only get the.
Which
Yes.
part of memory starts at low addresses and grows with calls to functions?
Oh no.
Can't see the answer.
Yeah, this is gonna be tough.
It's gonna be blue.
Who's got better internet?
Oh, this is sad.
Okay. My first. I don't know.
And it ended. Oh
So on our phones, it only shows the shapes that we can pick.
Oh.
It doesn't show the question. So we just have to wait until the question shows up on the screen.
Okay. I will for now. I'm gonna. Can I kill the music to just Kahoot? Yeah. I will read off the answers as best as possible. So the next 2 questions, it's going to be the same answers as the first one here. So you can pick based on. So code segment is red, data segment is blue, heap is yellow, stack is green.
Okay.
So, nice work, Lizard King and Alpha Number that got the question right. So next up, which part of memory starts at high addresses and grows when the program calls a function?
Okay, hopefully they're in the same position too.
They are in the same position, yeah.
Okay.
Yeah, it took it. Yeah, it took it.
Look at that reaction time.
Yeah.
Okay, nice. So most of you got it,
Yes.
despite the latency issues. So this is the stack is the thing that grows downward from high addresses. So nice. And got some climbers. Lizard King still in the lead.
Oh yeah.
Next up, same answers. Which part of memory contains global variables?
Oh crap. Oh.
Right. So I'm gonna put a dead word on there.
Damn, I wish I had Google Fiber right now.
What were the answers again?
gotta get
Code
that
segment is
BIOS.
red, data segment is blue, heap is yellow, stack is green.
About to kick all my family off the internet so I can have.
Yeah, I do have a gigabit connection, but I have no idea what my upload is, so it might also be my internet. So,
Okay.
Yeah.
Ooh.
So
Good.
yeah, the answer here is the data set.
Yes.
Most of you got it. That's what contains global variables. It would contain constants and things like that too as well. I forget what's next. Okay. What part of the compilation process fills in addresses from outside libraries?
Is it the
And
same?
red is
No.
red is compiler, blue is linker, yellow is loader.
Wait, red is
What was the
compiler.
question again?
What part of the compilation process fills in addresses from outside libraries?
Oh, you said compiler, linker, and
And
I just
loader.
need. Crap. Duh.
Ooh, actually not sure.
Okay. So we got most of you got one of them. So the linker and the loader are both responsible for this to some extent. The linker, if we have something that is statically compiled in, so if we're linking against like the C standard library, the linker can fill in the holes where we know we're going to call a function from that library, but we don't know the address of that yet. The linker can statically link that in. Or if we're doing dynamic loading, we're using a dynamic library, then the loader fills in those holes when we load the program. So either of those is correct. The compiler doesn't really deal with outside libraries. It just deals with the program itself. Okay. Nice work, Lizard King. Stayed in the lead there. Okay, next up is 3 true falses in a row. So true is blue, red is false.
Just click one side.
So true or false, operating system manages the data stored in the cache.
So you said blue is true?
Yep.
And red is false? Okay. Ooh, I forget. What?
Okay.
Well then.
That's
Oh,
the false.
no.
That's all hardware based, the cache.
Yeah, so the cache is a hardware thing.
Oh.
It's built into the hardware that when we fetch something from memory, it gets stored in the cache at a certain spot, but the OS doesn't actually interfere with that process at all. Trick question. Okay. Next up, true or false? An optical disk takes longer to access than main memory.
Awesome. This takes long.
Oh.
Damn it, peanut butter. Is it Tyler?
Yeah.
Okay, nice. So yeah, it's true. Optical disks tend to take a lot longer to access. So that's going to come up when we start talking about virtual memory. The original virtual memory was like this really slow variant that stored things on disk whenever you ran out of actual like physical RAM to use. It's like the first computer we ever owned was like an Apple II, and it was always interesting. So like it would start saying like there would be a pop up that says like running out of physical memory, starting to use virtual memory, and then it would basically just like the computer would be unusable because it would start storing things to disk instead of in RAM, and it was just like so incredibly slow that it didn't really even matter that it had virtual memory at that point because the optical disks were so much slower.
Okay.
Peanut butter taking the lead.
Oh, finally. I had a rough start.
So true or false? System calls are cheap because they switch from user mode to kernel mode.
I could lose it here, honestly. I'm going to lose it.
Cheap?
The system calls it cheap.
They don't cost a lot of money.
Damn.
Cheap meaning like performance wise. Okay, nice.
Oh, wait, what?
Right, so system calls are expensive, right? They switch from the switching from user mode to kernel mode is why we don't want to have a lot of system calls. So, okay, let's see the results.
Boo.
I didn't get to answer the last one. That was weird.
Oh,
It's okay.
I'm the only one who missed it.
Zzz in last place or in third, Peanut Butter in second, and Lizard King came back and took it at the end.
Nice.
So,
Sweet kitty.
nice work. I feel like it's probably not the best idea for me to like mail you candy. both the Naval Academy and like maybe the FBI might start wondering what I'm doing if I do that. So I will owe you candy when you come back, or if you're a senior. Sorry.
Solid.
Hopefully you'll be there at some point when we get back onto campus. Who knows when that'll be, but yeah, I will owe you candy at some point. So the rest of you I will have for something else, I assume. Okay, so I know it's a little laggy, so I'll try to keep that in mind when I'm doing things on my screen here. I do have a sort of document camera set up to try to draw some stuff, and then otherwise we're just going to be going through the notes. These are linked on Piazza, so if you want to either open these up and follow along or make a copy of your own so you can fill in the blanks yourself, whatever works for you is fine. These should be on Piazza under Chapter 9 notes. Any other administrative stuff that I wanted to talk about?
There'd be like a filled-in version once we're done.
Yeah, there will be a filled-in version. We'll post that at some point. It'll just be this, but with the blanks filled in. I will be filling these in as we go. So if you want to just sort of follow this document and keep track of what we're talking about this way, that's fine. I know it's a little bit different than being in class. I like having the printed out version there. So it's up to you what helps you learn. Whatever helps you learn is best. I will also say, if something isn't working in terms of, the format of lectures right now, please let me know. I'm happy to try other things. If you, have another class where something's working really well, let me know that as well. We're sort of, as a department, keeping track of what we're doing, so, we'll have some check-ins in terms of, seeing what other people in the department are doing. But if you have another class that's doing something particularly useful with online learning, please give me that feedback. And obviously if something's not working, like the stream, or the notes are not showing or something like that, like really not working, then definitely let me know real time so that I can fix it. So okay, so moving into chapter 9. So chapter 9 is all about memory management. We're going to be looking at how the operating system deals with the fact that we have all of this physical RAM and we have multiple processes that we want to map into that RAM. So we've talked about how to decide which processes to let run, which ones to schedule, but now we need to know how do we divide up that physical DRAM among these processes. So memory is, as we've talked about before, a huge array of bytes, and each of those bytes has its own address. The total number of addresses is determined by the number of bits that a computer uses to store those addresses. So you may have heard of the terms like a 32-bit machine or a 64-bit machine, or like if you go to download a program, you'll see download this for 32-bit Windows or 64-bit Windows, and that's because those are two different addressing systems. So these applications are built for using either 32-bit addressing or 64-bit addressing. So the number of addresses that we can support is equivalent to how many bits are in each address. So how many addresses do we have in a 32-bit system?
32.
Just 32 minus 1.
So this is, we have 2 bits each, right? So 2 to the 32?
Minus 1.
Minus 1, right. This is just 2 to the 32.
Wait, what?
Or no, you're right. Yeah, 2 to the 32 minus 1, sorry.
Okay.
Yeah. So if we had 2 to the 32 minus 1, that gives us 4 billion addresses, right? Move formatting.
Byte addressable, or is that individual bit?
This is individual bytes, right? So we can use each bit to generate an address, and that means that we can address 4 billion different bytes in the system. So we're just using a byte for each, or we're using one of these addresses that we can generate with 32 bits to address each byte. So we can address up to 4 billion things. This is roughly equivalent to 4 gigabytes of RAM. And we always kind of have to assume that we, have a little bit of overhead for like the OS and things like that. So in a 4 gigabyte system or a 32-bit system, the maximum RAM that we could have is 4 gigabytes. Because we at max have 4 billion addresses that we can use to address that RAM. So this was the reason that we sort of transitioned from these 32-bit machines that I had growing up to 64-bit machines that we have now, because we just couldn't physically address as much RAM as we needed to be able to address in these new systems. So like you couldn't have an 8 gigabyte machine with a 32-bit system. So what about 2 to the 64 minus 1?
Ooh, that's big.
It's huge. So 2 to the 64 minus 1 should be 1.8 times 10 to the 19th. Which is roughly equivalent to 256 terabytes. Has anyone used a 256 terabyte RAM machine?
Not yet.
Yeah,
Someday.
I don't know that, even the Cray supercomputer that we have, I don't think that would even have 256 terabytes of memory.
You could get close to it. Those big Optane DIMMs we were looking at were 1,024 gigabytes a piece, so those were a terabyte a piece, but you still couldn't even put a dent, I guess.
Right. So it's a lot still, but you would still need 256 RAM sockets in a machine, which is a lot. So, I'm sure there are systems operating on the 256 terabyte scale. Like if you look at some place like, IBM Deep Blue or something like that, those sort of machines are probably using that much memory, but it's distributed over a bunch of different machines. So each individual machine is not using all of that. They're using, whatever number of gigabytes they have, or maybe a terabyte of RAM, and then they're splitting up those addresses among all the machines. So the point being that most modern machines don't actually support 64-bit addressing. Despite the fact that we call them 64-bit, they're really 48-bit. Because that's 256 terabytes is 48-bit, so this is even larger. So 48 bits allows us to support 256 terabytes of main memory. And essentially, like for all of the infrastructure that we have in this machine, like the cache support, the registers, all of this other stuff that we have, instruction formats, everything like that would have to support 256 or 64 bits if we use 64-bit addressing. And so it's cheaper for us in terms of the hardware design to just use 48-bit addresses and to not deal with the fact that we could actually have 64 bits worth of RAM. And this 256 terabytes is enough in 48 bits for now at least. And then once we get to the point that we can support more than that of RAM, once we have Optane and things like that a little more dense than they are now, then we can support 64-bit addressing and add the extra transistors that we would need to support that. So any questions so far? Okay. We want to make sure that the memory used by the OS and memory used by user programs are protected from each other. We want to make sure that when we allocate these processes into memory, so something like we see at the bottom here, when we have the OS running in that same memory, that we want to make sure that these processes don't interfere with each other. So question here is, do we want the hardware to provide this memory protection, or do we want the software to provide this memory protection? So would it work for software to prevent processes, like if the OS in software tried to prevent processes from interfering with each other, would that work? Or how would that work?
And the OS could assign pages to a certain program?
Could assign pages to a certain program? Possibly. So that is how it works under the covers. I think you've probably gotten into virtual memory from advanced architecture, but we will get to that, how it actually does it. So let's if we had the OS responsible for managing memory protection, so we have processes allocated to certain memory regions, we want to make sure they don't go outside of their memory regions. Could the operating system handle that task, and what would it have to do that?
And it'd be having to get like feedback from like the memory itself of like, or being able to like query the like memory, the DRAM for like where a program lies, which would just be a lot of overhead, I feel like.
Yeah. So we could also think of like the fact that, you know, when does it have to check that something is going wrong here? Like when does the OS have to check that a process is not reading or writing outside of its memory space? Like what type of instruction would it have to check on?
Every read or write.
Load or stores.
Yeah, every load and store would have to be checked to make sure that this process is not writing outside of its memory region, which is rough, right? That means we're going to be doing a check every single load or store that occurs, which is just not going to be feasible in terms of the software overhead. So it's much more efficient for the hardware to do this.
Makes sense.
So instead, if we have the hardware managing this, we can basically check every single time that a load or store happens. The hardware can check to see, is this within the base and the base plus limit of that process. The OS is going to set those base and base plus limit for the hardware, but the hardware then can do all the checking and make sure that it's not actually going outside of the bounds. So that's the main benefit of using hardware to provide memory protection, and we will use that. So this approach is called segmentation. Where have you heard the word segmentation before?
Whenever my program crashes.
Segment faults.
Yeah, whenever your program fails, right? So this is sort of an old term. But yeah, if you see a seg fault, that's what this means, is a segmentation fault. So you have gone outside of the base and the base plus limit of your program. And then the OS or the hardware has thrown up thrown an error, and the OS catches that and forwards it along to your program. And then your program exits, right? Because this is something that we don't want to allow to happen. So before it happens, the hardware throws this error and doesn't allow you to write over some other process or write over the operating system. So it's a bit of an outdated term at this point because we don't actually use segmentation anymore. We use virtual memory instead, but the segmentation fault term has still just sort of hung around as like you've gone outside of the bounds of your program in memory. But this is what it used to look like, is we would have this sort of operating system processes, and each process would have a base plus limit. The issue with this is, of course, that you're limited in how many things you can run at one time. So once we have these three processes in memory, we have the OS in memory, we can't run anything else, and we have to sort of move a process completely out of memory, pull something new in, and we'll see today that there are a few other issues with this as well in terms of using contiguous allocation. So any questions on segmentation? Okay. So using segmentation, we can sort of quickly check that the process or each address being accessed is within the limits of that process. So downsides for segmentation. I just talked about one that, it sort of fills up memory and leaves no space for anything else. We have to deal with the fact that, like, if we are running a process and we want to stop that process now, we can no longer just make that context switch as easy as, like, changing some register state, right? So we've talked about context switches being, like, we swap out the registers, we save them somewhere, we record the PC that the program was at, we record this very minimal set of context, but if we have all this stuff in RAM, now if we swap out a process, we either can't use that RAM or we have to like do something really expensive like saving all of the stuff in RAM to disk. So that's obviously not okay. So this sort of fills up memory, doesn't allow us to map multiple processes into memory. We're sort of tied by what is already using memory in terms of what we can actually run on that system. And so if we try to run a program, we don't have any space in memory. We just have to put that program in the wait queue or in the ready queue sort of indefinitely until memory is ready for that process. So final sort of background thing that we need to cover. So the book talks a lot about address binding. So address binding is the process of like taking your program and mapping the variable names in that program, the functions, everything else, to actual physical addresses in memory. Right? So when you write an application, you write function names, you write variable names, you use those functions and variable names in the source code. When that actually runs on the system, we need to know that your function foo is actually at address OX deadbeef or something like that, right? And we need to know that variable int x is actually at address OX 04 plus the stack pointer or something like that. So it's related to where the stack pointer is, but it is at some address. If this is a global variable, we need to know that it's at a specific address in memory again, so OX 0800 or something like that. But we need to actually bind these addresses to real physical addresses in memory when we run that program. And so this happens at a couple different places: compile time, load time, and execution time. So at compile time, we can bind anything that is within our own program. So if we have local variables, we can figure out where they are on the stack. We can figure out where globals are going to go in our data segment. However, we have to keep in mind that like the data segment, the stack, all of this stuff may end up in a different place when we actually load the program, right? So if we look back at this chart here, where we see these processes in memory and the OS in memory with a base and a limit, we can see that like the process at the bottom is mapped from 256,000 to 300,040. The other process is mapped after that in memory, but we could see a situation where we swap those two in memory, and they end up in different places. And if that happens, now their addresses are all going to be different. So we can't always assume that the addresses that we put into our program, given a sort of segmentation approach, we can't assume that where we put things in our program is where they're actually going to be in memory when this runs. So we have to write programs or build these programs with a compiler and linker and loader, knowing that they may end up being placed somewhere else in actual physical memory. So at compile time, we can take anything that is sort of static to our program. So bind, local variables to stack addresses. These are going to be relative to the stack, and otherwise that's pretty much all we can bind at compile time, and we can leave holes for the linker. So the linker is going to then be able to, go to statically linked libraries, things like that. And fill in those holes best as possible again. But if we're using an approach like this, load time is where most of this work is going to have to happen. So when we decide which chunk of memory we're going to place this process into, we have to update all of the addresses that are in that program to match whatever place in memory we put that program. So we're going to bind addresses, bind basically holes. Find these holes that we've left in the program to physical addresses. And there's a whole mess of stuff that happens here. Like if you ever look at the debugger like before your program runs, if you run GDB and like pause it right as as soon as the application starts, you'll see that there's a whole lot of stuff that happens before your application gets to your main function. And that's most of what this work is, so that when there is a hole somewhere left by the compiler, it loads up a library, and then it sort of patches together all of the addresses left by the compiler. And then at execution time, this is dynamically loaded libraries that we are going to patch up. And there again, we're sort of looking at patching up holes left by the compiler. This can also be if we move a process from one memory segment to another. So if we have this sort of setup where we have processes in regions of memory, if we do need to stop running a process or move it in memory for some reason, we would then have to repatch all of these addresses that we left behind because of the fact that we have a new spot in memory and we do have new physical addresses now. And we'll get into this a little bit more with virtual memory. So virtual memory to some extent eliminates this need. And we'll talk about this more in depth when we get to that part of the chapter, that virtual memory allows us to basically assume that we have the entire address space. And if we know that we have that entire address space, we don't have to do quite as much of this work. So we'll get to that later. Hopefully that'll be a little more clear at that point. So we also need to talk about virtual versus physical addressing, because we will get into virtual memory here. So the address generated by the CPU for a specific program is referred to as its virtual address. So that's essentially saying, like, this is the particular application. It has its own addressing scheme that may or may not reference the actual physical address on that machine. So this is what my sort of older computer did. When I was telling you about the Apple II that we had, it would have this virtual addressing scheme where you could have more memory than the actual physical DRAM that you had. So if you had, at that time it would have been like maybe 4 megabytes of RAM. You wanted to have an application that could use an unlimited amount of RAM. So if you're using AOL Instant Messenger, or so not even AOL Instant Messenger back then, AOL Online, and playing trivia or something like that, if it started to use more than that 4 megabytes of memory that you had for some reason, it could then put some of that memory on disk. And that meant that you could have a larger amount of virtual addresses than you had physical addresses. And so you might have virtual addresses that don't actually exist in physical memory, and then the operating system has the task of sort of mapping those addresses from the virtual space to the physical space. So we have this virtual address that is what the program uses, and then we have the physical address, which is what the hardware actually sees. So the hardware has this physical address that it uses to actually access DRAM, to pull things into the cache, to pull things into registers, to actually do the loads and stores, but that's not what the program actually refers to. So the program almost never refers to the physical address. It's only going to refer to the virtual address. And this allows us to manage this abstraction from virtual addresses to physical addresses in the OS, and allows us as programmers to not really know anything about the DRAM that we're working with, right? Like, I mean, most of the time you never really think about how much RAM you're going to have on a system when you write an application. You just think about the fact that you need to do something in particular. Maybe at the last stage, if you're trying to optimize for some huge server cluster, you think about how much RAM you have. But for the most part, you just think about the fact that you're accessing memory, not how much memory you're accessing. Okay, any questions so far? Cool. Okay, moving on. So final bit of stuff before we get into contiguous allocation, which is dynamic linking and loading. We have a couple options when we write code. We can sort of link these libraries in statically. So like let's say we're using libc, so we're using the C string library, the standard IO library, the standard lib, whatever headers we're including here. These are all built as libraries into our system. So we can either link these in statically, or we can link them in dynamically. And there's sort of pros and cons to each situation. So with static linking, we essentially build that library into our code. So we end up in the situation where we have, basically, can I insert shapes here? No, I can. So with static linking, we'd have something like this, where we have sort of our, original code, and then we have libc sort of attached to that. So this is, our program's there, and we have libc linked into our program. And that's huge. So the benefit of this is that it is included. So whatever version of libc we wanted to use is now there forever. The downside of this is that this is larger, right? We've now sort of built in libc. So one of the cons of static is that we get larger executables. Pro is that we have the correct version.
You do that? Are you like loading the entire library, or can you load parts of it locally?
I think you're mostly loading the entire library. You could probably do it that you try to sort of excise the part that you want, but that's a difficult task just because a lot of these libraries end up having things being very related to each other, or like using the same functions, things like that. And they are sort of compiled down into binary format, so it's hard to find what particular piece of the library you want to include. So I think mostly what happens there is that it is just one big application that includes the entire libc in this case. So the upside here is we have the correct version. Any other upsides that we can think of here for this?
Nope.
So in terms of address binding, is this easy or hard?
Hard because you have more things.
Hard because we have more things. Maybe. It is larger, so you're definitely taking up more space, but I don't know that it's harder because we have more things to link against. It would take a little more time to sort of search through and find things, though. But I think that falls under larger executables. So what about like address binding? Like when could we do this address binding? If we have things in libc that we want to bind to.
You do it when we compile it.
Yeah, so like when we compile and link it together, because this is static, this is happening when we compile the program. So link at compile time instead of runtime is a bit of a problem.
Oh, so it's like less overhead when you're running it.
Right. So if we have dynamic, then we have to sort of have this off to the side, and we have to find these things when we run the program.
I'm sorry, we still have landlines. And they're literally everywhere.
It's okay.
I can't beat all of them.
So our other option is we have, our program here, and we're going to link that to a, libc that is outside of our application. Oops. So we have libc over here now. We're going to link it to that libc that exists outside of our application. So that's dynamic linking. We sort of have this version that exists on our system, and we link to that at runtime. So we load whatever version we have on our Linux system, or if this is a Windows application, or our Windows system, that would be a DLL. On Windows, if you've ever seen that file type, so DLL is dynamically linked library. So that would be what you would load in Windows. That's sort of the equivalent thing. These are .sos. I should maybe edit that real quick if I can. So this would be libc.so. Here we would have libc.a on a Linux system, as the way you can sort of differentiate between the static and dynamic versions of these libraries. And they're basically just set up to enable either static or dynamic linking. So that's the file type that you'll see.
Is the library loaded at like when the program launches, or is it loaded on like the first instance where the library is called?
At this point, it would be loaded on the first instance where the library is called. So we don't actually know that we want this library in advance. I mean, I guess we could indicate to the OS that we're going to use it. But here, what's going to happen is, the first time we try to call this library, it's going to load it and sort of patch things together in terms of the address bindings. Yeah, good question. So benefits here. What are our benefits, our upsides of doing dynamic linking that we could think of?
There might be less overhead if it turns out we don't need the libraries.
Right.
At
So if you
runtime.
don't end up using the library there, so like if we've compiled in a bunch of extra libraries, and maybe as a user, you're doing the most simple thing that this application could do, you may not end up actually using the dynamic. You may not end up using that library code that's been compiled in. So more efficient. So it'd be like more efficient for larger applications that don't use everything available to them. And obviously the usual thing here is that the fact that static linking, the con is that it's a larger executable. Dynamic linking means we can have smaller executables. So cons.
Runtime.
It's going to be slower at runtime.
Yeah, slower at runtime.
Yeah. That's going to degrade performance. I mean, if that's what you care about.
Right. So we are going to have to load these things at runtime. We're going to have to figure out where the addresses bind to within that library that might be somewhere else in memory, or will be somewhere else in memory. What about versioning?
You talking about like having out-of-date libraries?
Yeah, so like on my Linux system, I upgrade to a new version, and libc gets patched. So now I have libc 1.0 and libc 1.5. Which one am I going to use?
But wouldn't it default to the newer one?
Well, it depends. Is my program written to use the API that is built into 1.5?
Oh yeah, maybe not.
Right. So APIs can change, and that means that we have versioning issues when we use dynamically linked libraries. So we might have to have multiple versions. That means that when we look at this in memory, we might see multiple versions of dynamically linked libraries. We might have like libc 1.0 and libc 1.5 loaded into memory at the same time, because we're not sure which one each program is going to use. We have multiple versions stored on disk then a lot of the time. So like if you look through your Linux systems, or if you look through your Windows systems, you'll often find libraries that have multiple versions stored on here. In fact, this is a big issue. Like if you've ever run anything that needed, I forget what exactly it was called, the like Microsoft Visual Studio libraries, essentially. That these would be like they had a runtime that you would use to run things built in Visual Studio, and so a lot of Windows applications will, say you need to have version 2.4 of this runtime so that you can run this application. And if you have the wrong version, then you have to go download a new one, and it's always harder to find older versions and things like that. So if you're not statically linking in your libraries, that means that the user then has to have the correct version of your library that you're using installed on their system. Whereas if you statically link it in, then they have everything they need to run your program by just downloading your application. So here there's not sort of this is an it depends situation again, as usual, that there are pros and cons to both. It depends on what you're trying to do. Most applications tend to use dynamically linked libraries nowadays, but there are benefits to using statically linked libraries as well. So especially this sort of usability aspect, not having to make sure that the user has this special version of the library that you need to be able to use. So just to keep in mind moving forward that these two things do exist, and that you will see these sort of different file types, and may run into situations where you want to compile things to a library in the future. Okay, so I think that's a good place to stop for today. We can get into contiguous memory allocation and some of this other stuff on Monday. So again, let me know, please, if there's anything that can help out with making this a little more smooth transition to online learning. Otherwise, we'll resume reading quizzes for next week's classes. I will get those out as soon as possible today, just to make sure that we are getting everything we need. And otherwise, I think everyone was here, so I'll check and make sure with Kahoot, but we had 11, so I think we're good. So thanks, everyone, for showing up, and good luck with the rest of your transition to online education.
Sir?
Yes.
Sweet.
I do not have my textbook, and I didn't